Good morning, everyone, and welcome to today's session. Today, we will be discussing about statistical methods in R, exploratory to modeling. So, we will be covering from exploratory analysis to statistical modeling using R. So, as most of you are from statistics background, it will be easy for you guys to grasp the details of R programming for statistical method because you already know the theoretical part and all, and some of you might be familiar with the processes as well. Okay, so as you all know, R is a powerful open source programming language and environment specifically designed for the statistical computing and graphing. It offers a wide range of built-in functions and extensive package that facilitate every stage of the data analysis process from data handling, which we have already seen, modeling and high quality visualization. So we have also seen the visualization part, but we didn't go on through the analysis modeling part. Now, um, in academia as well as the industry, R is widely using due to its versatility, and we can handle different the versatility include handling the different type of data like importing, cleaning, structuring and manipulating data from different sources like CSV, SAS, SPSS and databases, etc. Then we'll having a better library for descriptive statistics, calculating measure of central tendencies, dispersion, skewness, kurtosis, etc., etc. Then also for inferential statistics, performing hypothesis testing and all, we have a good number of functionalities and all. When it comes to statistical modeling, it is also having a good number of packages to handle different statistical analysis and all, and even the researchers and all, different researchers from the field of statistics and related field, they are also contributing their research work and all to R as well. So we have a wide variety of packages and abundance of the R functionalities for statistical analysis. So when it comes to exploratory analysis, we have already seen some of the exploratory analysis part. So that involved summarizing, visualizing data to understand the data. Then for statistical modeling, um, we will be starting from the linear regression, then generalized linear models, time series analysis, machine learning and all. So for everything, we have extensive packages for that, and our statistical capabilities are enhanced by these packages like stat, mass, lme4, foca, then carry. Okay, these are the main packages we use for the statistical analysis. So when it comes to exploratory analysis also, we have different parameters or different tools available for these things, and R provide functions for descriptive statistics, data visualization, data transformation and all. Some of the functions are explained here, so you can relate these things to what you already know. And then when it comes to statistical modeling, for linear regression, we use the LM function. Generalized linear model, we will be using the GLM. A mixed effect model, LME4, we will be using. Time series analysis, we will be using forecast. Machine learning, we will be starting with the carrot one, and then we will be using the random forest and all. Then model diagnostics and validation, we will be performing summary, ANOVA, plot, predict, etc. Now, when it comes to advanced statistical method, we can also do the advanced statistical methods like survival analysis, multivariate analysis, Bayesian analysis, etc. So for those things as well, we have several functionalities available. with that introduction, we'll be yeah, starting with the data part. So first we will be starting with the descriptive analysis, because when we getting some data, first we need is just explore the data. So basic exploration of the data, that is one thing we need. So first we will be starting with the descriptive analysis. For that we will be having some data. So I'm just creating a sample data here. So this is just for a sample. So we can calculate the mean for the data using mean function. So that will give you mean value. Okay, so once I click mean, it will give the mean of these values. Similarly, median we can calculate using a median function, and it will give you the median as well. Okay, so median is also there. Now we want to calculate mode, but for mode we don't have a direct function in R. So what we will be doing is like we will be calculating mode as like this in R. Okay, so we will be taking names of table of data. First we will create the table of this data. So that will be okay. So this will give you the frequency like this. So currently we don't have any repeating value, so I'm just creating some repeated values as well. Okay, so I just updated the data like this. So mean will be changing, median will be changing, and now we have a couple of the variables are repeating. Okay, few variables are repeating. So this is the method we follow for mode in a one line method. Otherwise we can write a function and calculate the mode. So first we will be use the table data. So table data will do a table giving the frequency count. Okay, so for the frequency table we will be using the function table. Now if you sort this one, okay, if you sort this data, okay, okay, if you sort this data, so sort this data, it will be coming like 10, 20, 12, 13, etc., etc. But it is in ascending order, but we need it in the descending order of the values. So then only the highest frequency will come. So we will be using the descending equal to true. Okay, so it will be in the order of frequency. Okay, you can see it is ordered by frequency. Now we want the first element to be taken from this one. Okay, so we want to take the first element. So here you can see it is actually showing you 3. Okay, it's actually showing you the 15 is the point and corresponding value is 3. Okay, but we don't need this 3 or the number of frequency we don't need. So for that we what we will do is we will be only taking the names. Okay, names of this one. Okay, so we only need the name of the frequency table. So name will be 15, but you can see here this is actually coming in a quotes. So as it is in quotation, it will be a character. Okay, so we don't need it as a character. So what we will do is we will use it with a numeric one. Okay, so we will be using as dot numeric. Okay, as dot numeric we will be using, and that will give you the numeric value of the mode. Okay, this is a one line function we can use for calculating mode in R. Okay, so that is why we are using this function here. So this is mode. Okay, this is how we calculate mode in R. Okay, Now, at least couple of you might be think like why there is a no direct mod function. So R does not have a built-in statistical function for mod because a mod can be ambiguous. Okay, and R has a mod function, but that is has a different technical purpose related to storage object. Okay, um, so couple of the reason R doesn't have a direct mode function is because first one is the ambiguity of statistical mode, like mean and median, which is result in a single clear defined value. But mode doesn't give that kind of a value, so it actually might have some multiple values, or sometimes it fails and all. So those kind of things are there. So that is why mode doesn't have a function, separate function. Second thing is we have a alternative mode function in R, in base R, that is actually a function return a internal storage type of data. Okay, so if I put a mode function, mode of data, so it will give us numeric. Okay, it will give us numeric because it's showing the storage type of the data. It's the data is stored as a numeric type. Okay, so that's why it is not. Then ease of user defined function. So like we can use table, unique, which max. So these kind of function. Uh, so using those function, we can actually calculate this one. And focus on the quantitative data. R was strong focus on the quantitative data rather than the qualitative data. So that is also a reason for no mode function is there. Okay. Now, next one is standard deviation. So for that we use the ST function. ST function will give you the standard deviation. For variance we will be using the var function. Okay, so that will give us the variance. For range we can use the range function as well. Okay, so that will give you the range as well. Okay, so range we will be getting the minimum and maximum values. Then we will be having interquartile range. Uh, For that, we will be using the IQR function, which will give you the interquartile range, that is Q3 minus Q1. For quartiles, okay, for quartiles also we can, for quartiles also we can use the quantile function. Okay, so quantile of the data will give you the quantiles like minimum value, first quartile, median value, third quartile, and maximum value. Okay, so these things will be taken. This can be taken from these functions, and we can also calculate the summary using summary function as well. Okay, using summary function, we will be getting the summary of the data. So that will be having minimum, Q1, median, mean, third quartile, maximum value for a numeric data. Okay, and then uh, okay, so for categorical data also we can calculate summary. So I'm just creating a category here. Okay, so summary of categorical data will give you the summaries like frequencies only for each category. The frequency only it will give. Now, if you want to have the frequency table, you can actually use the table function for frequency table. So that will give you a frequency table like this. Okay, Now you can also use the proportion table. So proportion table will give you the proportional values. So that will be like this. What is the proportion of each values? You can also use the cross tabulation, and that will give you the cross tabulation values like this. Mm, okay. So here there's a category 1 and 2. So it will show you the cross tabulation value of category 1 and category 2. Okay. Now proportional crosstab, same. Proportional crosstab, we can keep the crosstab function inside proportional dot table, so it will give you the proportional values for crosstab. Okay, what is the proportion of each value? So these are the basic descriptive statistics option we have in R. Okay, and now we will be moving to inferential statistics. Okay, so first, we will start with the t-test. So most of you might be aware about the theoretical part. So I don't need to explain the theoretical part and all. Okay, so what is the use of a t-test? Use of a t-test? Anyone can even unmute and say, or you can put it in the chat as well. What is the use of a t-test? Why we are using a t-test? So nobody is answering. I'm audible, right? Just wanted to check. Hello? Am I not audible? Hello, guys? Am I audible? Okay, yeah, thank you. So if you don't respond, I think sometimes it will be like will get confused. Like you're not hearing me also. Okay, so I was audible throughout, right? It's not from now. Actually, could you confirm? Like I was audible throughout, right? Yeah, thank you. Perfect. Yeah. Okay. So we were asking for t-test. Okay. So as you all know, like t-test is a hypothesis test in R as in statistics, and it is used to determine whether means are significantly different from each other. Okay. So when we use a t-test, we use a t-test when you are comparing the average and if the size is small or sample size is small to moderate, we will be using t-test. Then population standard deviation is unknown and data is approximately normal. Okay, these are the assumptions in t-test. what we are testing in t-test. Okay. uh, in in a one word, what is actually we are checking using t-test? So in t-test, what we are checking is, in a practical perspective, we are checking if the difference what we are seeing is real or just a random noise. Okay, that is the concept we are checking using t-test. This is very important because in some interviews also there will be some tricky questions. So you can always keep in mind in t-test what we are what we are checking, okay, is what I'm seeing is real or just because of random noise. Okay, that is what we check in this hypothesis test. Now there will be different type of t-test are available, like one sample t-test that help us to compare the mean with a common or non value. Okay, then independent t-test is there, so that is also known as two sample t-test. So it compare the means of two independent group. Okay, it compare the means of two independent group. And then we have a paired test also, paired t-test, that compare the means of the same subject before and after. Okay, same subject before and after. So it should have the same teams. Okay, or same subject. So this test statistics, as you already know, it is basically the observed difference minus expected difference divided by the standard error. That is what uh, we put it in the equation, like x bar minus mu divided by s by root n. Okay, so it is actually the observed difference minus expected difference divided by standard error. Okay, that is also important. If you want, I can put it here. Mm, okay, that is observed difference minus expected. Okay, so it is basically observed difference minus expected difference divided by standard error. So this is the formula. Okay, this is the concept we use in t-test. Uh, okay, okay. So we can also call it t equal to x bar minus mu divided by s by root n. This is the basic theory. Okay, where x bar is the sample mean and mu is the expected difference or hypothesized mean. S is the sample standard deviation, and n is the sample size. Okay. Now we'll be using the one more thing is that is important. Why it is important? Degree of freedom will be n minus 1 for uh, t-test. Okay. Degree of freedom will be n minus 1. Okay. Why degree of freedom is important? Why degree of freedom is important? You want to answer why it is important to know. You all are statistics students, right? Can anyone tell me what is the Basically, degrees of freedom ത്തിന്റെ ഏറ്റവും വലിയ യൂസ്, the main purpose of the degrees of freedom is basically it will define the shape of the sampling distribution. Okay, exactly, Fahima. That is the answer. So it actually define the shape of the sampling distribution. So if you are using the T distribution or F distribution or chi-square distribution, this degrees of freedom, that is the shape parameter for the sampling distribution. Okay, it will also determine the critical value, directly impacting whether you accept or reject the null hypothesis, and ensure the precision of the statistical analysis that is there. But more than that, it actually determine the test distribution shape or sample distribution shape. That is the main purpose of the uh, degrees of freedom. Okay, and this degrees of freedom is used to calculate the p-value also. Okay, along with the critical value, degrees of freedom will help us to determine the p-value as well. Then as Gauri mentioned, like degrees of freedom represent the number of values in a data set that are free to vary after some parameter are estimated or it will give you the independent values. Okay, like fewer degrees of freedom means more consistent, affecting how much uncertainty is there. Okay. Mm, that is the use of degrees of freedom. Okay, this is important when it comes to your applied level and all. It will be very important why you are using each of the concept. Okay, now we will start with each of the t-test. So first we will be starting with one sample t-test. That is basically, okay, I'll be putting a data like data one. So this is a sample data. So I can actually do the t-test with this one. So here the hypothesis will be h naught mu equal to some value. Here mu equal to 6, and alternative hypothesis will be h1 mu not equal to 6. Okay, and for test we can use the code like t dot test. Okay, t dot test, and d1 is our data, and mu, that is the assumed mean or hypothesis mean, so that is 6. Okay, so we are checking is this data follows with the um, average value or mu 6. Okay, now if you look at the t-test output, okay, this will be the output. So here we are having a few important points, like one is t value. Okay, this is the t value. T value is simply 1 point, sorry, 0.49283. And we also have degrees of freedom, that is 4. Here we have 5 observations, so degrees of freedom is n minus 1, that is 4. And we also have the p value. Okay, p value is 0.648. Now the alternative hypothesis here is true mean is not equal to 6. So h naught will be true mean equal to 6. Okay, so here we have a 95 percentage confidence interval, and the confidence interval values are fall between these two values. Okay, and so the mean can vary. The assumed mean 6, that is the assumed mean, and it can vary from 5.16932 to 7.194. Okay, now then we have the Samples estimation mean of x. The mean of this actual values is 6.18. So here t statistics is here. So that is the calculated t value measure measures the size of the difference between the group mean, size of the difference between mean from the actual value. Okay, so that is what the t value mean. Now we have the degrees of freedom. So degrees of freedom, as you already know, like the degrees of freedom will give you the related to the sample size. Okay, n minus 1 will be the degrees of freedom, and it determine the specific t distribution using the used to calculate the p value and all. Okay, and it will also give you the shape of the t distribution. Now p value is there. This is the more dependent value for a data scientist. So p value is the probability of observing a sample mean as extreme as or more extreme than one in your data. Okay, if the null hypothesis is true. Okay, that is what p-value means. It is the probability of observing a sample mean as extreme or more extreme than the one in your data. Okay, if the null hypothesis is true. And then we have the alternative hypothesis, that is the like alternative to your assumed hypothesis. It states the assumption about the population mean if the null hypothesis is rejected. Okay, here our null hypothesis is mu equal to 6. If it is rejected, alternative hypothesis mention like what is the population mean. Okay, what will be the population mean or its character when the null hypothesis is rejected. Okay, so then 95% confidence interval is there, that is the range of value which the true population mean are likely to fall within 95% of the time. Okay, so within this limit the average value will fall. Okay, so when we calculate the average value, it is actually 6.18, which is in this range. Then the mean of the data, that is the mean of actual data. Okay, so this is the values. When we come to the t value, how we interpret the t value. So t value, when a larger absolute value of t statistics suggests a greater difference between the sample mean and hypothesis mean. Okay, then degrees of freedom, a high degrees of freedom generally um, give means a more power to the defect. Sorry, more power to the power to detect an effect. Okay, if a higher degrees of freedom, there will be more power when we find out some effect in the test. And p-value, as you all know, like the center value for decision making, basically in data analysis at least. Um, when it comes to most of the data analysis problem, we consider the p-value. If the p-value is less than 0.05, you reject the null hypothesis. In this case, means are significantly different. If p-value is greater than 0.05, you fail to reject. We won't say we will accept. We will say, a statistician, we will say we fail to reject the null hypothesis, or there is no enough evidence to say that means are different. Okay, so here p-value is greater than 0.05, so we can get the call. Then alternative hypothesis confirm the specific test perform when the t-value when the hypothesis null hypothesis fails. Okay. Mm. Also, this confidence interval also we can use to determine um, the result is statistically significant if this confidence interval does not contain the hypothesized value. Okay, if the confidence interval does not contain this value, okay, this hypothesized value, then we can say that the confidence interval result is statistically significant. If it contains the uh, hypothesized value, that is mu equal to 6 in this case, then we have to do further check for making sure this result is statistically significant. Okay. So basically, when it comes to the interpretation, usually we look at the p-value of the test, and means as a data analyst, we will be looking at the p-value of the test, and if p-value is small, that is less than 0.05, we have a strong evidence that the sample mean is significantly different from the hypothesized mean. The confidence interval will not include in the hypothesized value. Okay, so if the p value is less than 0.05, you can also check the confidence interval is not included the hypothesis value. Okay, this is not included. Now if the p-value is large, if p-values are greater than 0.05, in this case we do not have enough evidence to conclude that there is a significant difference. Okay, so the observed difference could due to a random chance, and the confidence interval will include the hypothesis value. Okay, so that is the interpretation of this result. Okay, any questions here regarding the interpretation or these basic assumptions and any concept? Okay, I was not explaining this in a theoretical way. I was just explaining the concept in a more like um, data analytics perspective. If you have any questions, you can put it in the chat or you can unmute and ask. Any questions? Okay, I hope it is clear then. Now we'll move to two sample t-test. Okay, or we call it as independence t-test. Okay, now I am creating another. Okay, I'm creating a D2 and sorry, D2 and D3. Okay, we'll use a different data. Okay, so I'm creating in D2 and D3, and I can use the test as this t dot test d1 equal to d2. Okay, so our hypothesis will be d1 mean equal to d2 mean. Okay, mean of first data set equal to mean of second data set. So this is the test, and once we look at the test output, it will be using the Welch two sample t-test, and the result will be like this only. So it, it is more kind of a similar to the one we have seen earlier. So the interpretation is similar. T statistics is the defining that critical value. Then degrees of freedom is there, that is used to look up the critical value or find the distribution. Then we have p-value. So as usually we say, p-value is less than significant level, like 0.05. We reject the null hypothesis and conclude there is a statistically significant difference in both the data set. So here p-value is less than 0.05, so we can conclude that there is a significant difference in two data sets. Okay, so you can observe in these values as it is a small value, there is a significant difference. If p-value is greater than 0.5, we usually um reject the null hypothesis. Sorry, fail to reject the null hypothesis, like the difference is not due to the chance. We'll say difference is not due to the chance. Now we have the confidence interval here. So you can see that in this criteria, p-value is less than 0.05. So we reject the null hypothesis, and you can see this confidence interval does not contain the hypothesis mean. Okay, or the means here. Okay, and one more thing is like here when it comes to these values when it comes to a two-tailed test, okay, or sorry, not two-tailed test, when it comes to independent t-test, actually we need to check if p-value is less than 0.05, the confidence interval should not include the contain 0. Okay, if it does not contain 0, it confirms the finding that there is statistically significant. Okay, from confidence interval also we will be looking at this value. If 0 is there, or it include the mean of the distribution. If 0 is not there and means of the two populations are not included, then we can simply say like the test is statistically significant. Okay, it's not only looking at the t value or p value only. We need to consider the confidence interval as well. Okay, sometimes if the p value and all will be close to 0.05, okay, if it is very close to 0.05, sometimes we'll be interpret the result based on the p value. But in that case, we must need to check the confidence interval. So, because sometimes this confidence interval can have a great impact on your response. Okay, so every time before the interpretation, you need to consider these things. First thing is check the p-value. This is the most crucial part. A value below 0.05, we need to or that actually indicate a significant result. Then we need to examine the sample estimate, like actual means to, we need to look at the actual means to understand which group is higher or lower. Okay, so here the second group is actually having performing higher and the first group is performing lower. Okay, um, that is the result. Okay, here. Mm, oh, okay, okay, okay. Sorry, sorry. There is a one small mistake. So it is actually D2 and D3. Okay, okay. Now the result change. So, yeah. Here also the value is less than 0.05. Okay, p value is less than 0.05. So there is a significant difference in these two. But here also you can see the confidence interval. The confidence interval is actually not containing 0 here. Okay, it's not containing 0 or either of these values. Okay, so it is statistically significant. Uh, okay, so here you can see first group is actually performing or it is having a higher mean, and second group is having a lower mean. So first group is performing better and than compared to second group. And also we need to review the confidence interval. Okay, so four things we need to review is, first thing is the p-value for sure, and examine the sample estimates, like these estimate to understand which one is performing higher or lower. Then we need to review the confidence interval to check the condition, like if this value containing 0 uh, for a two sample test. Okay, for two sample test we need to check if it is containing 0. If it is containing 0, then it is not statistically significant for a two sample test. Then if it is one sample test, make sure that sample mean, sorry, hypothesis mean, h not the mu value, that does not include in this confidence interval. Then okay, the final thing is report the result using the t statistics, degrees of freedom, p value, etc. Okay, so these three values need to be present in your report. Based on these three values, with the help of confidence interval limit, we conclude that this result is significant or not. Okay, that should be your interpretation. Okay, it's not only looking at the p-value, because most of the time uh, when people are coming for interview and all, they are making this mistake. They will be, if we give some scenario or give some examples, they will simply look at the p-value and they know, okay, p-value is less than this, this is this, and p-value is greater than this is the. So it's very tricky. You need to look at the p-value, you need to look at the confidence interval, you need to look at the um, hypothesis as well. Okay, these three values will have an impact on your result, not only p-value. And most of the times when you guys are going for interview, the result, that will, the p-value result will be very close to zero point 0.05. So it will give you a confusion. Okay, so yeah, that is the thing. Hope it is clear. If any doubt is there, please feel free to ask. Okay, if nothing is there, we can go with paired t-test. So I'm creating a sample data here. Okay, now I wanted to check similar to here, but it is a paired t-test. So t dot test d4 and d5, I'm passing my two data set. I'm giving paired equal to 2 for creating a paired t-test. Okay. So this is d4, d5, and data essentially constant. Mm, error in the data. Okay, d data. Okay, let me put some other data. D4 equal to this one. Is it because D3 and D2? Okay, so it is actually checking the rank, so it is not taking that point value. Okay, that was the problem. Sorry. So here, okay, it is actually checking this one paired. This is actually checking the paired one. Okay, so it is actually checking something before and after. For example, here some parameter before and after. Let's say the okay, we are using the same data. Let's say the let it be the HbA1c levels before this one. And yeah, so this is the two diabetic parameters, let's say HbA1c level before the treatment, after the treatment. Okay, let's keep it like this. Okay, so we have the hypothesis like uh, T T test, T dot test, D3 and D2 paired. So we'll put it in this way, D3 and D2 before and after we are checking. So we are checking before and after if there is any significant difference. Okay, now we can also do this formula in this way as well. T test 4, that is equal to T dot test. So we can actually do it in this way as well, not mentioning paired equal to true. Okay. Mm, okay, then it should have some levels. Okay, so if yeah, that we will discuss when it comes to a real data. It is actually when you have a level in like before and after will be in D2 and D3 will have some values, then we can use this scenario as well. Okay, so that we'll discuss when we come with the data. So as of now, we can check this one. Okay, so So here we have this test, a pair t test, and we have this one. Okay, t value is 4.7472, degrees of freedom is 4, n minus 1, and p values greater than sorry, less than 0.05, and so we there is a significant difference between the group, and the confidence interval is also there. So uh, okay. So these are the parameters. Can anyone interpret this uh, pair t test? Can anyone interpret? Feel free to unmute and say. There is, we reject the null hypothesis. There is a significant difference between both means. Mhm. Okay. There is a change before and after treatment. Okay. So, okay. Like I said, the interpretation is not only depending on the p-value. Like it is a conclusion. Like there is a significant difference before and after. But that is not the interpretation. Interpretation is actually uh, more detailed one. Okay, so here the null hypothesis is true mean difference between paired samples is zero, and Alternative hypothesis is the true mean difference is not equal to 0. And when it comes to the t statistics, we will calculate the t statistics. And when it comes to degrees of freedom, it will be n minus 1. Okay, that is determine the shape of the uh, parameters. Like it will be always pairs, number of pairs minus 1. Okay, then we compare the p-value to determine the significant level. Like if p-value is less than 0.05, we reject the null hypothesis. Here p-value is less than 0.05, so we reject the null hypothesis, and there is a significant evidence to conclude that the average difference between two paired measures is statistically significant and not due to the random noise or random change. Okay, that is very important part when we uh, interpret the result. Okay, the change is not due to the yeah pre, this is not due, the change is not due to the random noise. Okay, it's not a random change, it has a statistical significance. But if p-value is greater than 0.05, we fail to reject the null hypothesis that there is no evidence to conclude significant difference between mean. Okay. Now, also we need to interpret the magnitude and direction when it comes to a pair t-test. So that is a sample estimate. Here the mean difference is 2. If the value, this mean difference value here, that indicates the average difference between the pairs in your sample. Okay, so 2 is the average difference between the pairs in sample. So there is a significant difference between the pairs. Okay, so so this is actually indicate the average difference between the pairs in your sample. And it will depend, sometimes sign will be also there. Sign is actually depending the order we have entered. Okay, and then we have the 95% confidence level for pair test as well. This provide a range value which the true population likely to fall. Okay, this is the area the true population mean likely to fall. If the interval does not contain 0, it reinforces the conclusion that the difference is statistically significant. Okay, this if this is not containing 0, the difference is statistically significant. Okay, statistically significant. Okay, here if we look at the p-value, we reject the null hypothesis, and there is a sufficient evidence to conclude the difference is not by random noise. Okay, and confidence interval, that is does not contain 0, so that is also statistically significant. Now in pair t-test, when it comes to pair t-test, we will use a ad hoc test, that is coherence d as well. So coherence d, it is not in this default output we are getting here, but it is often reported to understand the practical importance of the findings through coherence d. So we will find the coherence d for pair t-test. It is actually using the package called effect size. Okay, I'll tell you the importance of this as well. Okay, so mm, now we have the coherence d value for this pair t-test. So here d estimate is 2.36. which is actually large. Okay, here it is mentioned it is large. So if the effect is small, okay, I'll mention this. Effect size is small, d will be less than zero point 0.2. Okay, if the d value, the Cochrane's d value is less than zero point 0.2, the effect size will be smaller. If the Cochrane's d value is zero point 0.5 or between zero point 0.2 and zero point 0.5, it will be a medium effect. And if the Cochrane's value is large, it will be greater than zero point 0.8. Okay. If the value is greater than zero point 0.8, the effect is large. Okay, so while considering the paired t-test, we need to consider this effect size as well. Okay, this is an ad hoc test for paired t-test. Okay, this is very important. Mostly in your, I don't think in your academics you won't go through the effect size and ad hoc test for every test. Okay, so this is also important. And when it comes to the interpretation of this paired t-test, okay, so based on these two factors, we usually do the interpretation. But here, what we can mention is, okay, I'm not writing this. So here, the paired sample t-test indicate that there was a mm, here. What is the result? Okay, so there is a significant difference, evidence to conclude that the average difference in the average uh, before and after, or we can say as we have the HbA1c values, we can say that this paired sample t-test indicate that there is a significant evidence to conclude that the effect or the difference between the two paired samples, the treatment, the HbA1c level before and after have a significant difference. It is not due to a random chance. Okay, and the significant difference is statistically significant. So when it comes to the difference, there is a difference. Um, there is a decrease in the score from before and after treatment. Okay, and the mean difference was 2. Okay, the mean difference was 2. This is also important to indicate in your interpretation. There is a significant difference before and after treatment, and the difference is statistically significant and not due to any chance. And there is a mean difference uh, of 2 point with a 95 percentage confidence interval, for the true mean of 0.75 to 3.24. Okay, so this much thing should be there in your interpretation. And we also did the Cochrane's d, so we need to add one more sentence there. The Cochrane's d estimate also satisfies there is a large effect of the treatment. Okay, there is a large effect for the treatment. Okay, that is also one point you need to mention in your interpretation. So this much should be there in your interpretation. So what you have put it in the chat, it is actually good you put it in the chat. But for your information, this is just the conclusion. Okay, so what you have put it in the chat is just a conclusion. It is not a interpretation. Okay, be aware about the different terminologies. So what you put it in the chat, when Gauri and Aditya they put it in the chat, it is just a conclusion, not an interpretation. When it comes to the interpretation, you have to mention like This pair t-test indicate that there is a significant decrease in the HbA1c level before and after treatment. So there you can mention these t value. Okay, or if you want, I can write it here as well. Um, okay, significant difference in HbA1c level before and after treatment. So there you need to mention these three values. Okay, and the mean HbA1c level before treatment was 8.85, while mean HbA1c level after treatment was 6.18. Okay, the effect size of Cochrane's D was 2.45, indicated larger effect size. Before that, I need to mention one more thing. Okay, treatment. The average difference is statistically significant and not due to the random noise. Okay, noise. Mm, and also, okay, okay, 95%. Okay, so this much should be there in your interpretation. So for this pair t-test, this pair t-test indicate that there was a significant difference in the HbA1c level before and after treatment, and you have to mention these values here, because on basis of these three values we are interpreting this statement. Okay, we are interpreting this statement, or we are concluding to this statement. um, Now, the average difference is statistically significant and not due to any random noise. Okay, any random noise, because this is statistically significant as per the values here. And the mean HbA1c level before treatment was 8.18, while the mean HbA1c level after treatment was 6.18, and the mean difference was 2. Okay, mean difference was 2 with a 95% confidence interval for true mean. that is the actual mean, and that is 0.92 to 3 point okay, it is point not point 75 to 3.24. Okay. And Cochrane's d value was 2.36, sorry, 36, indicating a large effect size also. Okay, so this much should be there in your interpretation. This is very important. That's why I'm taking some time and explaining this interpretation as well. Because most of the time people won't put this one. Okay, this interpretation. They will interpret. If somebody asks to interpret the t-test, okay, you need to interpret this much. If someone asks you to conclude t-test, you can put the comments which you put in the chat, like uh, you can either say there is a change before and after treatment, or there's a or you can simply say the paired t-test indicate a significant difference before and after treatment in this case. Okay, so in that one sentence you can actually conclude the conclude the t-test. But if someone want to interpret you, you need to mention these things. Okay, this is the interpretation. So this is very important when you come to the practical scenario. Okay, so that is about the t-test. And okay, so that is with the t-test. And any questions so far? Okay, if there is no question, Perfect. Now we will see how we can perform the ANOVA. So how we can perform the analysis of variance in R. Okay. Okay. So what is analysis of variance? Can anyone unmute and say what is analysis of variance? So what is your understanding of analysis of variance? Okay, I will give you an offer. Like whoever is actually explaining this one, uh, the analysis of variance properly. So I'll give 1 point to your assignment. That 1 point will be like 4 marks. Okay, that's an offer. Yeah, and in between, like I have updated couple of assignments I have completed looking at it and share the grades. The remaining will be shared by today and tomorrow. Okay. Yeah. Okay. You can simply get a. Okay, Fatima, compare the means of two or more groups by analyzing the variance. Okay. Mhm. Any other thoughts? Can anyone unmute and speak? Anyone? Okay, no one want any marks, additional marks and all. Okay, that's good. Okay, yeah, thanks Fahima for answering. So you will get 4 marks. I'll note your nine. And yeah, okay. I'm glad that at least one answer. So great. Okay, okay. Now we will just talk about ANOVA first, and then we will move to other things. Okay, so ANOVA is a statistical method, as you know, that is used to test whether three or more group means are significantly different. Okay, it's not two or more group; it's actually three or more group are statistically different because if it is two group we can simply do the t-test or chi-square or so. Okay, so when it comes to ANOVA, we are testing whether three or more group means are significantly different. Okay, so we are checking means there. Now, what we are exactly looking at ANOVA is if all the group means are roughly the same or it at least one truly different. Okay, that is the question we are checking with ANOVA. Okay, if means all the means are roughly the same, all the group means are roughly the same, or at least one truly differ. Okay, that is what we are looking at ANOVA. Like what we have done looking for t-test was, is the difference I am seeing is real or just a random noise? Similarly, in ANOVA, we are checking all the group means are roughly the same or at least one truly differ. Okay, now ANOVA is kind of an extension to the t-test. Okay, so it's kind of an extension to the t-test. Uh, then why we are not using multiple t-test and we are going for ANOVA? Now, suppose we have a four group. Okay, suppose we have four groups. So, uh, if we have four groups, then we need six pair t-test to be done. Okay, and each test has significant level alpha equal to zero point 0.5, and there might be a combined error that may be increase. Okay, when it comes to the combined error for this six different analysis, that error can be very high. So and it will also lead to the increase or inflation in the type 1 error. Okay, it can lead to the inflation in type 1 error. So that's why we are not using multiple t-test and going for the analysis of variance. Now, there is a very important question. Okay, so the important question is why it is called, why ANOVA is called analysis of variance when it actually compare the mean. Okay, so it is a very important question, and most of the time people fail to answer this question. Okay, why it is called analysis of variance and when it actually compare the mean. Now, the core idea, means are actually compared indirectly by comparing the variance. Okay, so here the mean are compared indirectly by comparing the variance. So ANOVA, what ANOVA asking us is the variability between group means large compared to the variability within the group? Okay, so we are comparing the group mean based on the variability within the group or treatment. Okay, so when you looking at the ANOVA table and all, so you will be seeing we are comparing the treatment effect between group effect and all. So what we are comparing is the variation between the group, the mean variation, how the mean is varying between the different group or treatment. That is what we are comparing. That's why ANOVA is known as analysis of variance. It is not comparing variance, it is comparing the means, variation in means in different group. Okay, so ANOVA asks, is the variability between the group means large compared to the variability within the group? Okay, that is the question we are answering through ANOVA. And also analysis, it has actually means analysis of variance because we use the test statistics as F statistics. Okay, when it comes to ANOVA, we are using the F statistics at as the test statistics. Okay, so we are concluding this thing using F statistic. We are comparing the uh, different hypotheses using the F statistics and concluding the ANOVA. So that is also one reason why we are calling it as analysis of variance. It is not analysis of means. Okay, so even though it is actually comparing the means only. Now, so so when it comes to the ANOVA, one more thing is like the total variability in ANOVA is actually by two factors. We are comparing the between group variations and within group variance. Okay, so we are checking two things like between group variations or variance and within group variance. So between group variance will be caused by difference in group means, and within group variance will be a random noise inside a group. Okay, so so that's why we are called as and also variance rather than it is comparing just group means. Okay. Uh, so ANOVA basically compare the means between the group, but it tests them using the variance. That is why it is actually named as analysis of variance. Now, when it comes to ANOVA, we'll have multiple type of ANOVA, like one-way ANOVA is there, two-way ANOVA is there, repeated measure ANOVA is there, and MANOVA is there. All right. MANOVA is multivariate analysis of variance. Okay. So one-way ANOVA, as you know, one categorical factor will be there. In that factor, multiple group will be there. Two-way ANOVA, two factors will be there, like treatment and interaction effect will be there. Then repeated measures of ANOVA, there will be same subject, multiple conditions will be there. And MANOVA is there will be multiple dependent variables, so it will be a multivariate analysis. And when it comes to the hypothesis, so we will first detail about one-way ANOVA, then we'll go to the rest of the things. Okay, one-way ANOVA. So okay. So ANOVA hypothesis will be H naught all group means are equal. That is H naught equal to for K groups. Okay, for K group, H naught mu 1 equal to mu 2 equal to mu 3 equal to etc. up to mu K equal to mu K. Okay, an alternative hypothesis will be at least one group mean is different. Okay, now one important thing is when it comes to ANOVA, ANOVA does not tell you which specific group means are different. Okay, for that one, we need to do some post hoc test. Okay, so one of the preferred one is tuck is HSD. That is the preferred one. So here I am putting one example ANOVA for I have a group one, then group two values are there. Then I will have a group 3 as well. Now I have these three data points are there, group 1, group 2 and group 3. Now I wanted to perform an ANOVA, one-way ANOVA here. So for one-way ANOVA, what we will usually do is will create a model AOV, values against group. Okay, values against group, data equal to data frame of this one. So instead of this one, I can actually create the data frame above. So I have this group 1, group 2, group 3. So I can put this into a data frame. So data equal to, so I'm putting this one, data equal to data frame, value will be group 1, group 2, group 3, and group will be factor represent A, B, and C, each 5 times. Okay, so this will create the data, and my data will be look like this. Okay, so my data will be look like this. So A values will be in A, B, and C. Okay, so now I wanted to perform the analysis on variance ANOVA. So my ANOVA will be, we will use AOV function for ANOVA. So if you look at AOV function, okay, this is the AOV function in R. And when it comes to, first we need the formula, then data we need to pass, and then if any projections are there, like some logical flags are there and all, we can put those things. And if any QR decomposition needed and all, so we can put those things. And any other constraints are there, then we can use those things, and other formats also we can perform there. Okay, simply this is the function call, and you will get some examples here and all. So here we are using this one, this example, AOV value against group. Okay, we are checking the value against group. Our data will be data only, and summary of ANOVA result. Okay, summary of ANOVA result will be like this: group group will be, there will be two degrees of freedom will be 2 for group, and for residuals there will be 12 degrees of freedom, and group sum will be 13, residual sum will be 18. um, that sum of squares will be 13.33 and 8.404. Mean square will be 6.66, and residuals 0.7. And here you can see, as we discussed earlier, like in ANOVA we are using F statistics to test the hypothesis. So here we are using the F statistics, and F statistics value is 9.519 for 2 comma 12 degrees of freedom, and p value will be 0.0034, that is less than 0.05. Thus we reject the null hypothesis, saying that there is a significant difference between group. Okay, uh, now um, there is no significant difference between the group, as we can see here. Okay, so so here p-value is less than 0.005, so we reject the null hypothesis, and at least one method here has a different mean score. So all the means are not equal. Okay, here the hypothesis all the means are equal, that is rejected. So all the means are not equal, so at least one group has a variation. So here also you can look at the F value. If the F value is larger, the between group variance will be greater than within group variance. Okay, if F value is larger one, between group variations will be greater than within group variation. Now we can put this data into a visual perspective using box plot. Mm, okay, so we will be using the box plot to visualize the, Okay, we will be using the box plot to visualize this one. So here it will be okay, three groups. So we have box plot we have discussed yesterday. Value against group, and data will be data. Main heading will be box plot of group. X label will be group and Y label will be values, and columns will be light blue, and all. So let's plot this. So this is the group output. So here you can see that here one group B is actually having a difference here. Okay, group B is actually having a difference here, and yeah, we have all these things. Now we will now do the post hoc test, that is Tuckey's HST. Uh, so Tuckey's HST will determine how the group variations is actually happen. So here let's put the test and let's look at the result here. Okay, so this one, the Tuckey's HST test indicate which specific group were different. So here if you see B and A, okay, so okay. So B and A is there, that the difference is 2, and C to B is difference is -2, and C to A is actually difference is 0. So you can clearly understand, like here for this one, so C to A, that is actually difference is 0. The mean difference is 0. So C and A is okay. Like they are having the same mean, but the difference is actually with B. Okay. So difference is with B. So that is clearly indicated in the box plot as well. So here the difference B to A and C to B is not. So A and B and B and C, their interactions are not 0. Okay, so based on that two group, it is not 0. H naught of H naught mu A not equal to mu B. H naught mu B not equal to mu C. Okay, but H naught mu A and mu C are equal. Okay, that's why their difference is 0 here. Okay, so that is how we can interpret which are the group having differences in the box plot. ആ കഥവ് പുറത്തുനിന്ന് പൂട്ടിയിട്ട് നോക്കും, ഞാൻ എന്തെങ്കിലും ആവശ്യമുണ്ടെങ്കിൽ അടുക്കള വഴി തുറന്നു വരാം. എന്നിട്ട് താക്കോല് അവിടെ കൊണ്ട് വെച്ചു. Okay, so that is about the ANOVA. And any questions in ANOVA? Any questions till here? Okay, so the interpretation is as follows, like the one way ANOVA result indicate that there was a significant difference between the group, yeah, the three group, that is F statistic we have consider 2 and this one 12, and the F statistics value was 9.51. Okay, and p value was 0.00334. Okay, this suggests that at least one group mean is different from others, and the post-hoc Tuckey's HST reveals the group B has significantly higher mean compared to group A and group C. Okay, I'm not looking at these values now for now. However, there is no significant difference between group A and C because their p value is 1. Okay, there is no significant difference between group A and C, and the box plot is also visually confirm the same findings. So, okay, we didn't consider the effect size and also that is not necessary for this thing. So that about the ANOVA. Now two-way ANOVA. So two-way ANOVA is used to okay. Two-way ANOVA is used to determine how okay determine the effect of two independent variables on a dependent variable. It also helps us to understand if there is an interaction between two dependent variable on the uh, dependent variable. Okay, two independent variable on the dependent variable, and also hypothesis will be all group means are equal. That is mu one equal to mu two equal to mu three equal to etc. equal to mu k, and alternative hypothesis will be at least one group mean will be different. So it won't tell the which group is different, so we will again perform the Tuckey's HST. So here we are creating a random data set here. So I'm just creating a data that is equal to a data frame. So I'm creating some values, 60 random normal values. Okay, and of factors I am creating just factor 1 as A and B, and factor 2 as XYZ. Okay, 2010. So my data will be like this. Okay, so now my data is like this. So here factor 1 is A and B and factor 2 is XYZ. Okay, so there will be two different levels we need to consider and their corresponding values as well. So or I will put data 1 and data 1. Okay, now ANOVA we can perform the same way, AOV. So our dependent value will be value, and against the independent factors are factor 1 and factor 2, and our data will be data only. So if you look at the summary of ANOVA, we can see that the degrees of freedom for factor 1 will be 1 as there is only two levels. Factor 2 will be 2 as there are um, three levels. Then factor 1 2 will be 2. uh, and residuals will be there are 60 observations, so 60 minus 1, this one 2 2 4 6. Okay, 50 minus this minus 1, so that is 54. Sorry, 60 minus this 7 sorry 5 minus 1, that is 54. Okay, so that is the degrees of freedom we have, and similarly we can interpret the two-way ANOVA as well. So here the p-value is less than 0.05 for factor 1, and here the p-value is greater than 0.05, and here the p-value is greater than 0.05. So we'll also do the Tuckey's HST. Mm, Okay, we will perform the Tuckey's HST for this 2D ANOVA, and the interaction effect is actually as follows. Okay, we'll come to that, and now for Tuckey's HST, we will be do the interact sorry interaction plot, because box plot is won't be enough for Tuckey's HST, so we'll be doing interaction plot for this one. So interaction plot, we can do interaction dot plot, factor 1 factor 2 values, then main heading will be interaction plot, x label will be factor 2, y value will be mean value, colors will be different colors we put, layout will be okay. So okay, so now this is the interaction plot. Okay. Okay, so now this is the output, so we will just go through each of these things. Okay. And yeah. Okay, so here we can interpret the values result as follows, like here first of all we will having the ANOVA result. So if we look at factor, degrees of freedom will be here, like df1 will be for factor 1, degrees of freedom is 1 as we discussed, and for factor 2, degrees of freedom is 2, and factor 3, degrees of freedom will be sorry, factor 1 2 interaction, degrees of freedom will be 2, and for residuals interaction will be 54. Now p-value is for factor 1, the p-value is 2.05 into 10 raised to minus 11, so that is very highly significant. But for other two it is not significant, these two are not significant. So from this result we can conclude that factor 1 is highly significant, and strong evidence that mean differ across levels of factor 1. Now, factor 2 is not significant. No evidence that factor 2 affect the response on average. Okay. Now, factor 3, that is also not significant, or factor 3 is this one, interaction effect. So, interaction is not significant, and the effect on factor 1 does not depend on factor 2. Okay. So, now we went to the Tuckey's HST. So here Tuckey's HST is actually saying here B to A in factor 1 there is only two levels. So B to A, so mean of B is significantly higher than A. Okay, so that is why there is a significant difference in the mean, and difference is positive and large. This is fully support the ANOVA result we have here. Okay, we have here. So factor 1 is significant. Now, so for factor 2, all the p-values are greater than 0.05. So here all confidence intervals include the zero value. If you look at this upper and lower limit, it include the zero value. So no pair of factor 2 levels differ significantly, and it also matches to the ANOVA thing. But when we come to the factor 1 and factor 2 or the interaction effect, you can see some of the significance adjusted p-values are here. So for example, if you look at this one here, here, and these kind of few values are significant, and adjusted p-values are there. Uh, but if the interaction term is not significant in ANOVA, we should not interpret the Tukey's comparison for interaction. Why? Because there are exploratory constraints that might be impact this one, and overall interaction effect is statistically weak. Okay, so like here the overall interaction effect on factor 1 and factor 2 is statistically weak, so there is no meaning we compare the group difference using or result, sorry, interaction effect using Tukey's HST. Okay, and individual significant constraints can appear by chance only, because here we reject the null hypothesis. So these individual interaction can be appear by chance. Okay, so we won't interpret this Tukey's HST for interaction effect. Now the okay, now if we look at the plot here, the interaction plot here. So this plot, in this plot, it is actually A and B, and here on the, if you look at the lines here, it is not parallel. It is not perfectly parallel lines. So there is no effect on these two. So, and here some of the okay, it is not a properly parallel. So mm, here there is some interaction showing, but it's not parallel. So there is some contradiction, that is this is actually it is actually showing some kind of an interaction, but the ANOVA is actually contradicting that one. So there is a small visual differences are there, but that is not statistically, that is not saying like it is the results are statistically significant, and variability within the group is large enough to explain the this pattern. So that is, even though going through this interaction plot much, we can depend on the ANOVA result, or this ANOVA result, because this is actually an inferential one, even because and this plot is actually a descriptive one, so we can more rely on the result here. So that is actually saying the interaction effect is not significant. Okay, so in conclusion, we can say that the uh, two-way ANOVA examining the effect on factor 1 and factor 2, that actually the analysis revealed that there is a significant main effect on factor 1, um, and mean values are also significant, differ significantly between the factor 1 using the Tukey's HST, and the main effect on factor 2 is not significant, and that is confirmed by the Tukey's HST as well. the mean effect is very low, and the interaction between factor 1 and factor 2 is not significant, suggesting that the effect on factor 1 is consistent across levels of factor 2, and post hoc test is also confirming the factor 1 effect is consistent. Okay, but no significant difference observed among the levels of factor 2. Okay, when in Tuck is adjusting. Okay. So here, with this ANOVA, we can simply say that in this particular data, only the factor 1 matters, factor 2 doesn't matter to the effect. Okay, so that is the interpretation of this ANOVA. Any questions here? Any questions? Okay, now we will okay, so the interpretation is as follows, like this is the interpretation in short, and now we will move on to the okay, so this is the interpretation for this two. Okay, now we will move on to the chi-square test as we already discussed about the interpretation here. Okay, so now we will move on to the chi-square test. Okay, so what is a chi-square test? Why you guys are so silent, not responding? Okay, test using chi-square statistics. So what exactly the chi-square test is? Why it is using? Why the chi-square statistics is using, Aditya? To test the association between two categorical variables, to find the relationship between variables. Yeah, good. At least some of the comments are coming. That's good. To test between categorical variables. Okay. So one person told that it is to test the relationship between categorical variables, and one told the association between categorical variable. So which one is true? Which one is true? It is for um, is it for relation or association? Okay, Aditya is asking back to me. Okay, it's actually for analyzing categorical data to see if there is a significant between the observed result and expected result. Okay, observed and expected. Okay, but still, is it actually the relationship or association? So this is a tricky question. Like these kind of questions you can always expect in some tricky interviews and all. So actually, chi-square test is used to check if there is a relationship. There is a relationship which is also known as association in statistical terms. Okay, so basically, chi-square test is used to check whether there is a relationship between categorical variable. This relationship is in common term, and in statistical term, that relationship the relationship between categorical variable is known as association. Okay, so basically chi-square test will do the associations in terms of statistics. It's check the association between categorical variable. In terms of a common language, it is actually a relationship. Okay, so both are correct only. Now, most precisely, it actually check chi-square is actually checking the association or dependency, and it's not checking the causation. Okay, and only it will work with the categorical variable using the frequency counts. Okay, so chi-square is not checking or test the measure, or it won't measure the strength, or it won't compare any means, and it won't work with numeric data directly, and it only work with the frequency data. Then there are different type of chi-square test are there. One, as you know, chi-square test for independence is there. This is to check if two categorical variables are associated with each other. Okay, chi-square test of independence check two categorical variables are associated. Okay, for example, we can check if gender associated with smoking status. Okay, so those kind of association we can check with test of independence. Then we have chi-square test of goodness of fit, that is checking whether one categorical variable follows a specific distribution. Okay, goodness of fit test is for checking if one categorical variable follows any specific distribution. For example, does the die follows a uniform distribution? So that is using chi-square goodness of fit. And when it comes to the chi-square test for homogeneity, it actually check the different population have the same distribution. Okay, different population have the same distribution of categorical variable. Okay, that is chi-square test for homogeneity. For example, chi-square test for homogeneity. For example, yeah, do different region have same preference distribution or something like that? Okay, so that kind of thing we can check in chi-square test for homogeneity. Okay, the more common test we are using is chi-square test for independence. Okay, that is more commonly used chi-square test. So for basically there are three type of chi-square test: chi-square test for independence, goodness of fit, and homogeneity. In independence, we test the association. In goodness of it, we will check the distribution, and in homogeneity, we will check the equality across the group. Okay, that is the three things. Any question? Okay, any questions here? Okay. Now, chi-square test is used when we have the data is categorical, observations are in count, and if the observation is not in count, we will convert it into count using the table function, that is for converting the frequency table. Okay. Now, okay, first we will look at the chi-square test for independence, and for that one the h naught will be, sorry, h naught will be two categorical variables are independent, and h1 will be two categorical variables are not independent. So we will create a contingency table for that, and here the chi-square statistics will be um, summation O minus E the whole square divided by E, where O is observed frequency and E is the expected frequency. Okay, so one more thing you can check here: bigger the chi-square value, the greater difference between observed and expected value. Also, also we will get a smaller p-value. Okay, here we will also get the smaller p-value. Mm, okay, so that is also a point you need to uh, keep in mind. Now we will create a contingency table. So I'm creating gender. So I'm creating a gender, then let's put a um, preference or result. Okay, let's take some pass and fail result as well. So now first we need to create a if you look at this data, we will be having gender and result. So if I put it as a data, then it will be um, okay. If I put it in data dot frame. Okay, okay. So if I put a then data, then it will be a column like this. Data frame will be like this. But I cannot do a yeah, I cannot do a chi-square test using this data. So any data, first we need to transform it into a contingency table. So first I will be transforming it into contingency table using a table function. So I am giving table data gender and table data result. Okay, so I will get a contingency table like this. Okay, it's a 2 by 2 contingency table, as we have two levels in each of the categories. Now we will perform the chi-square test for independence. So we will simply pass this chi-square dot test and the contingency table we have created. Okay. Now we will get the result of chi-square test here. So here the chi-square is actually 0. Chi-square value is 0. Degrees of freedom is 1. And yeah, chi-square is this one. Degrees of freedom is 1. And p-value is very high. That is uh, yeah, p-value is very high. That is 1. So if the p-value is greater than 0.05, we fail to reject the null hypothesis. This is actually an overfit. When p-value is coming to 1 and all, we call it as overfit. So here, no significant association between gender and the result in this data. Now, we can also see the expected count. Here we already know the actual count. Okay, this is the actual count. We can see the expected count also. So for expected frequency, we can use chi-square test dollar expected. So it will tell you the expected frequency. So if you look at our data, mm, this is the expected frequency, and we got exactly the expected frequency. So there is no statistical significance. Okay, now this is the one. Sometimes actually what happen is here. If we look at the values here, so it's expected and actually is almost close. Mm, Here the expected frequency is less than 5. So in that case, sometimes the um, chi-square won't work. So in that case, we can actually use the Fisher's uh, extract test. So So as expected frequencies are all are less than 5, we will be using the Fisher's extract test. So that is one condition for this one. So okay, so for that we can use the Fisher's test, Fisher dot test, and we will be passing the contingency test, and we will get the interpretation here. So here, mm, here the thing is that p-value is again 1. So as we discussed earlier, like it is not, greater than 0.05. So there is a significant difference in all the categories. Okay, Fisher's test is also satisfying that. Now we will look at another chi-square example. We'll see. Okay, example 2. We will be creating an chi-square for independence. One more test. Let's create gender. Okay, I'm creating a few more variables here. Okay, let's split from here. So okay, so I'm creating this much values, and we will be creating smoker categories, and okay, so I'm creating gender, and if they are smoking, okay, category I'm putting. Now I can create a contingency table. So I'm creating a contingency table for this one. Contingency here. Okay, I'm just assigning. So table, gender, and smoker. So I'll be getting the contingency table as this, and we will be testing the chi-square for independence here. And this is how the chi-square independence test for independence here. And here also the p-value is 1. It's not. There is a significant difference between the category as the result saying. So now we will see the expected frequencies as well. Chi-square dollar expected. So that will be 12.5, 12.5 and all for all the categories. So we will just interpret the result. Here, the chi-square test indicate that there is a significant association. There is no significant. Yeah, there is a the p-value is 1. So there is a significant association. Okay, and there is no. Chi-square of is But actually, there should be some difference because here it is actually calculating the observed and expected. So there is a difference of 0.5. So chi-square should not be exactly 0. There should be some changes in the this one. Chi-square is 0, which means actually in this formula uh, O minus E should be 0. That is when chi-square value is actually 0. Here O minus E is okay. Sum of O minus E might be 0 because there is a 0.5 difference for all, and it will be added up to yes, yes. It will be added up to 0. Yes, correct. So that okay. So that is 0, and p-value 1 means the observed data are perfectly consistent with the null hypothesis. Uh, so there is absolutely no association between the categorical variables. The variables like gender and smoking status, that is actually variables behave. Okay. So here, the chi-square test indicates that there is no significant association between the gender and smoking status. Chi-square equal to 0, p and p-value is 1. So the variables behave exactly as if they were independent. Because I just got confused because here we see the expected count as 12.5 and actual count as different. So uh, the chi-square value will be 0 only if the O minus E is actually 0. So that's why I just got confused. But when we add up these values, add all the O minus E squares. So no, it is actually the squares, no, right? A point, there is a 0.5 difference, and if we add up all the squares, it won't be it won't be 0, right? Oh, let's put observed is 13. Okay, just a confusion. Let's find out that one. 13 minus 12.5 to divided by expected, that is 13. Okay, I'm just checking this. This is the first one, this one, and this one will be 12, 12 minus 12.5 square divided by 12. And here it will be 12 again. So it will be 12 minus 12.5 square minus divided by 12. Mm, sorry, 12.5. Sorry. 12.5. So 12, 12, 13, 13. Okay. Yeah, it's actually 0.08. There is a slight difference than 0. Okay. It's not exactly 0. It is actually put at 0 because Might be it is rounding to some chi-square value, so that's why it's rounded to 0. Okay, so okay, so chi-square table is also not having some kind of this values like integer values, so it can take actually any value, so it would be something like this. So it's not yeah, so there is a small variation from the actual one. It's close to 0, but it's not exactly 0. That's why I just um, came through that one. Okay, now okay, so here we have seen the chi-square. This is how we use the chi-square test. Okay, now it is not showing any groove changes and all, so there is, we are just checking if there is any yeah, we are just checking if there is any particular relations or association between the two category variable. Okay, now next one will be any questions here. So any questions so far? Any question from anyone? Any questions? No, right? Okay, so in that case we will be go to chi-square goodness of it. So the hypothesis will be H naught observed frequencies fit expected frequencies, and alternative will be observed frequency does not fit with the expected frequency. Okay, so we will be go to an example here. So we will be seeing the observed frequencies and expected frequencies. Let's say this one. Okay. Mm, now we can perform a chi-square goodness of test. So chi-square test observed, comma p will be expected divided by sum of expected. Okay, that will be a probability. So here we can see the chi-square fit. So chi-square is chi-square will be 5 degrees of freedom will be this, and p square p value will be 0.08. Okay, so that is greater than zero point 0.5. So we say that there is a significant yeah, there is a significant difference in between the observed and expected. Chi-square is 5. Okay, so chi-square degrees of freedom, no, 5, and mm, okay. So here it is not fitted with the expected values. So that is the interpretation. So we can this is about the chi-square test. Any questions to chi-square till here? Any questions? Okay, perfect. Then that is about the three major those things like three major test cases we use testing a hypothesis we use in data analysis. Now we will move on to the regression analysis. So first we will go to okay. So regression analysis. Okay. So now what is a regression analysis? What is regression analysis? Okay. Uh, okay, to find the relationship of one dependent variable and two or more independent variable. Uh, okay, to it is to display a relationship between two variables on dependent and on independent. Gauri, you are every time you are adding one more variable to the assumption. So it's actually we can do the regression analysis to find the relationship between one dependent variable and one or more independent variable. Okay, so it is not two or more independent variable. It can be one independent variable as well. Okay, so we can check the relationship between one dependent and one independent. So that will be simple linear regression. And if there is two or more independent variable, that will be multiple linear regression analysis. Okay, so yeah, factually you are correct. Like only the number of variables are different for both the comments. So it can be the relationship between multiple variables. It can be multiple. So there should be one dependent variable and multiple one or more independent variable can be there. Now my question is you might be heard about the term called correlation, right? So what is the difference between regression and correlation? In regression or correlation, we are actually checking the relationship. What exactly the difference between these two? Okay, so what is correlation? What is the difference between correlation and regression? Any thoughts? Okay, in correlation, we are checking whether there is a relationship, and in regression, it's a type of relationship. In regression, are we checking the type of relationship? Almost close, but not exactly the regression side. Correlation is about checking whether the relationship is linear or not. Mm, okay. Correlation. Okay, correlation find the relationship between the variables, while regression predict the relation to find one variable from another. Correlation measures the strength and direction of the relationship, while regression models that relationship to predict outcome. Okay. Very close. Okay, thanks for the inputs. So basically, correlation, we are using correlation to try, means or correlation to answer the question where x and y are, or are x and y are related. Okay, correlation finds like are x and y are related. Okay, so this is the question correlation try to understand answer. Uh, okay, not taking regression analysis. Now regression finds how does y changes when x change. Okay, so this is the question regression try to answer. Okay, so it is actually the simple one, but mainly when it's a simple question, but you might be familiar with the regression and correlation as well. But whenever people we are asking for the change or difference between regression and correlation, many people actually stuck. Okay, this is the main difference between the correlation and regression. Correlation try to answer are x and y is related. The other point you have mentioned is very correct. Like mm, for regression analysis, we used to predict and explain the variables. Correlation, we only check the or only measure the strength or strength of association. And when it comes to this one directional thing, so regression is directional one, but correlation is non-directional. Okay, so okay, so regression is actually directional in terms like I think Fahima means the direction means this plus or minus sign, but that is not the direction exactly. So direction is like what I mean is regression has one-way relationship. That is from x to y only we are checking the relationship. From using x, we are trying to find the relation on y. Okay, so x is actually defining the relation on y, but correlation is non-directional. Like it actually we can for x to y or y to x, we can actually find the relation. So it's non-directional when it comes to the correlation part. And variables in regression, there will be independent and dependent variable, but when it comes to the correlation, there is no independent or dependent variables are there, so it's both are depend to each other. Okay, so then when we look at the results of a regression model, we usually get in regression model we usually get Okay, so this is basically the things. Let me comment out these things otherwise. Okay, okay. So when we look at the output, actually in regression it will be an equation, and in correlation it will be a single number, that is correlation coefficient R. And range regression can take any real value, but correlation will only vary between -1 to 1. Uh, Casualty, like we can actually use a casual assumption, or we can model a causality in regression, but not in correlation. In regression we can predict, but in correlation we cannot predict something. Okay, so yeah, so that is a markdown I just created. So this is actually the relations. Mm, I can also mention something, some example here. So okay, I can put the statement like height and weight are related when r equal to 0. Let's say 87. Okay, so there is a high association between height and weight. Now in regression we will be interpret it like this. So like, okay, weight increase by 5.5 kilogram for every 1 centimeter increase in height. Okay, this is the kind of interpretation we do from the regression analysis. Okay, so okay, correlation basically measure the strength and direction of a linear relationship between two variables, and on other hand, regression models the relationship between dependent and uh, one or more variable, one or more independent variables, allowing for prediction and understanding of how the change in independent variable affect the dependent variable. So this is actually what regression try to answer. Okay. Mm, okay, so the thing is like this direction is not exactly this direction. So this direction is uh, regression is actually one unidirectional, like it only using x we model y. But in here correlation it is not unidirectional. Like we can either, if we look at the correlation between x and y, or y and x, it will be same. Okay, so I'll just x, so x comma y equal to correlation of y comma x. Okay, so just to space here. Okay, okay, so it is like this. Okay, so it is two directional thing, so not the exact one. Okay, so here that is a relationship between regression and correlation. Now, okay, so first we will think about one correlation, then we will go to the regression. So there are different type of regressions are available. So type, simple linear regression will be there. So that will be one dependent one independent variable. Then multiple linear regression is there. So that is having two or more independent variables. Then logistic regression is there. That is a category or binary variable one. So it is the target variable will be binary. So it's a classification model, not a regression model, basically. Then polynomial regression will be there. So in polynomial, like it will be nth directional polynomial. It can be any polynomial, not a linear one. Okay, it's should not be a line. It can be any this one. Then ridge and lasso regression are there. So these are actually technique used to prevent the overfitting. That is a common cause when we are actually using regression analysis and all. Then we will have a stepwise regression. So that is a method to fitting model which choice predictive variable is carried out by an automatic procedure. Okay, so use the step to do that. And so these are the main one, and one quantile regression is also there, that is focusing on estimating the conditional median or their other quantiles response to this one. And then after this, non-linear regressions are there. So some of these is already covering the nonlinear regression. Then time series regression is there. So for the time series data, we will be using the time series regression analysis. Okay, now before we start to this one regression analysis, so also an important thing is we need to consider the assumptions of regression analysis. Okay, so there will be assumptions for linear regression. First one is linearity. That is the relationship between independent and dependent variable should be linear. And second one is independence. So the observation should be independent. Okay. Then third one is homoscedasticity. So that is actually mentioning the constant variance of errors. Errors should follow a constant variance. Then normality, errors are normally distributed. Okay, or residual should be normally distributed. Then no or less multicollinearity. So every time we cannot say that there will be no multicollinearity. So we will be in practical situation we will be considering low multicollinearity as well. Okay, so multiple regression, the independent variable should not be uh, too highly correlated with each other. So then no autocorrelation. Okay, that is only for the time series regression analysis. Okay, with these assumptions, we can go to the linear regression examples. Okay, any questions so far? Any questions so far? Okay. Okay, I think it is clear for everyone, and we'll be starting with the regression analysis. So first we will load the necessary libraries, ggplot2, car. Okay, so I will install car. So car is actually for this is like the basic regression functions for like the model diagnostics, and also for those things actually we are using the car library. Okay. Um, okay. First, we will do a simple linear regression using a sample data set. So let's load the library, and so I'm creating a sample data set. Height will be some random values. Weight will be based on height. Okay. Weight is the dependent variable on height. So here we actually create a direct one. So it will be um, unexpected symbol weight. Okay. So now to fit a simple linear regression model, we are using the LM function. So what is LM function? So LM function is simply fitting the linear model. So first we need to provide the formula, then data, then any subset if we needed, or any weighted models we need, we can share the weight. And uh, so NA action, like what should be if the data contain NA values, then method we can put which method we are actually using, um, and all. So then model XY or QR. So what is the model we are using? Then other constraints as well. So you can also find some yeah, also find some examples here as well. And what is the output of the regression value? So we will be getting a coefficient vector, then residuals we will be getting, then fitted values we will be getting, rank we will be getting, weight, residual values, call function, like what is the call we are using, what is the formula we used, then what are the terms we used, then contrast, x levels, offset, x, y, that is the input values only. Then what is the model, then what is the NA action we have done. Okay, so these are the output we are expecting. So this is some examples here. Mm, okay, so okay, we will do one thing. Before moving to regression, we will be look at some examples for correlation. Okay, so let regression be there. We will first see some examples for correlation. Okay, so first we will see some examples for correlation. Okay, let use the height and weight itself. Height. Okay, I'm simply putting some random values here for correlation analysis. So height and weight I have created. Correlation, for correlation we can use the COR function, and I am just passing the height and weight. So I'll be getting the correlation. Correlation between height and weight will be 0.99. So it's very close to 1. So we can, there is a strong correlation between height and weight, that is 0.99. Okay, so it's a strong positive correlation. This is how we can check the correlation between two variables. Now for regression, we can actually use the regression model. We will simply use the LM function to create a regression model. And weight and height, weight against height, we use the tilde symbol here, and we are passing the data. No other things we are passing, just a simple linear regression model. Then we will be checking the summary of the model. So the summary of the model will give you these things. So this is the model summary. Okay, so now we will interpret this model summary, how this model is actually contributed. Okay, so what are the important factors of the model summary? Okay, so what is the important factors of the model summary here? Here, first we are having the call option. So call option is actually letting us know like what is the formula we used. Okay, so here we are used linear regression weight against height. Okay, weight is our dependent variable and height is independent variable. Okay, now here we have the residuals as well. The summary stat of residuals are given like minimum, maximum, minimum quartile, median, sorry, minimum first quartile, median, third quartile, and maximum values are there. So from this one, we can simply looking at this points, we can. This is the 5 number statistics. Using this one, we can simply understand the distribution of this one. Roughly, it is actually centered to the value 0. Both positive and negative values are there. So it's actually a good sign. Like it's starting from -9 to maximum and positive 10. So it's actually negative and positive values are there. That's a good sign, like there is no bias and all between the values. Okay, so these informations are actually getting from this simple output, because sometimes now when people are interpreting, they will simply skip the residual part and all. We can simply understand the distribution of the values and all through the residuals itself, not from the plots and QQ plot and all. So we can also get a rough idea from here. This is actually uh, okay. Mm, okay, let me put it here. So it actually used the um, okay, this actually fit the model like weight equal to beta naught plus beta 1 times height and plus a epsilon error term. Okay, so beta naught and beta 1 are the coefficients. Okay, okay. So this is the model we try to fit here as well. So I'm just putting that one. Okay, now we will go to the next one, the coefficient table. So in coefficient table, we have the intercept value also there, and high uh, related to, sorry, related to height. There is some parameters also there. So this is the more important, more important table or vector we are having in the regression analysis. So here, by these values, we can okay, by this value we can simply interpret this one, uh, the fitted model weight equal to, okay, so weight equal to, it is not this one, so I'm just updating 1 point, sorry, it's 0.515 plus, sorry, minus 1.93. Okay, weight equal to minus 1.93 plus minus 0.515 times height. Okay, so this is the interpretation we have here. Oh, it's not minus, it's positive only, sorry. Okay, this is the model. This was the initial model here, and this is the final model. And one more thing, this is very important when more like 90 percentage of the statistics students are not aware about the same. So what exactly here we fitted a regression model. What exactly happened when we term something like a model fitting? Okay, so here uh, we need to fit this model. So simply the model fit means uh, it is just to okay, it's just to find the coefficient or unknown parameter in the model. Here in this one, the unknown parameters are beta naught and beta 1. So a model fit simply means we are trying to estimate that parameters beta naught and beta 1 that minimize the sum of squares difference between the observed predicted values of it. Okay, so it's a detailed one. Okay, so basically a model fitting means we need to estimate the parameters, unknown parameters, that is beta 1 and beta 2, sorry, beta naught and beta 1 in this case. Okay, so that is what a model fitting means. So regression model fitting means simply we are trying to fit the values or estimate the values of beta naught and beta 1 in this particular example. Okay, so that is the case. Now, so here it was the statistical formula for a regression model, and here this is the model. Okay, this is the model equation. This is the statistical equation for the regression simple linear regression model. This is actually the regression model for this data. Okay, so that is there is also this difference. Like, what is the difference between a model and equation? So first we have the regression model. So based on this equation, based on this statistical formula, we estimate this model, or we created this regression model. This is the model and this is the formula. Okay, now we need to interpret this one. So here intercept is yeah, intercept value is minus 1.934. So that is expected the weight when height is equal to 0. Okay, when height is 0, this should be the weight. Okay, when height is 0, and the weight should be negative in this case, so that is not a meaningful in real life. Okay, now p values for this particular one, p value is actually 0.818. That is not significant, but it's actually fine that intercept p-value to intercept is not that important in real scenarios and all, mostly. Okay, it's mostly, not always. So that is also fine, but this estimate is not meaning, it is actually meaningless. So when the um, height is 0, we cannot say that there will be a negative weight. Okay, so that is actually not a practical case, but as per the model, this is the value. Now, for height, when we come to the height, the coefficient value or beta 1 value will be 0.515. That is for every 1 centimeter increase in height. Okay, every 1 centimeter increase in height, weight will increase by 0.515 times. Okay, or 0.515 kilogram weight will be increased every 1 unit change in height. Okay, now here the p-value is significant. This is highly significant. uh, this is actually here you can see the star symbols. So here it is 3 star. 3 star means it is having a strong evidence. Okay, so this is very strong evidence. This is also a good evidence. This is kind of it is actually satisfying the condition, but these three values, it is not satisfying the condition. Okay, so that is how these values intercept. So these three values are good, satisfying the condition, and these three values are not satisfying the condition. Okay, now, so this is actually this one. Now we have the r square values here. So we will see multiple r square is 5.2 and adjusted r square is 5.1. So about 52% of variation in weight can be explained by the variable height here. Okay, that is what it interpret. So from here, uh, around 52 percentage of variation in weight can be explained by this height variable only. Okay, so that is not a good r square because it's mostly zero point 0.5. So sometimes we say in real life, we say like if the r square value is zero point 0.5, okay, rather than going for a model, okay, it's actually saying that there is 50% risk. Okay, so it's this model is actually predicting 50 percentage or 52 percentage. So 42 percentage risk is there if you use this model. Okay, that is what this model actually tells you. There will be 42 percentage risk in this model if you use this model. Okay, so that is also one information we are getting from the adjusted r square and r square. Now now the thing is, do we need to go for this model? Often this leadership team, they won't consider this kind of model because they are saying if they go with some if they are having one problem, like let's say for Amazon, okay, Jeff Bezos is actually using this kind of a model to predict, do the price prediction in Amazon product. Okay, so he's actually getting adjusted R square like this, and he often decline this model, and he will go what his mind says. Okay, because if he is choosing a decision his own, okay, um, sometimes in practical situation, if in this scenario, like Jeff Bezos wanted to take this model, and he wanted to find out should he increase the price platform fee to from 5 to 10 rupees. Okay, that is his call. Okay, for that he is actually doing a regression model and finding out this model. So he is actually find a model with 0.52 percentage, okay, 52 percentage. So usually this business people say, like, here in this model we need to take 40 to 48 percentage of risk. Okay, only he applies this model, there is a 52 percentage rate of success. So he often won't go for this particular model. What he will do is he will go for his own assumption. Okay, he will say, okay, I will increase, because if he increase with his assumption, not going depending on this model, he's only taking 50 percentage risk. Okay, so if he put all the effort and some money to this modeling person, and he's only able to find out a 52 percentage accurate model, he would rather go for his own assumption. He can simply toss a coin and say take a decision that will give him 50 percentage confidence level. Okay, so that is also one aspect this leadership people actually go for. Okay, if they are not getting a proper model, they can take a decision by completely trusting on the luck or their mind voice and all. So they can simply go for that one, because if this model is accepted, there is 48 percentage risk. If a coin flips and take a decision, then they will have 50% risk. So why they need to invest this much money on creating this model? Okay, that is why we are tuning the models and making the models perfect. Okay, so here, this r square is actually 52 thing. So the correlation we can calculate. Okay. So here R square is, I'll just copy this. Okay. Okay. So correlation from R square is simply the square root of this R square. So that is simply um, okay. Okay. That is simply 72 percentage dependency on height. Okay. Um, Okay, so that is how we calculate correlation from the uh, adjusted R square, okay, or multiple R square like this. So this is actually square root of R square. Okay, so that is 0.72. That's a high correlation between the variables. Now, if you look at okay, here, if you look at the F statistics, okay, F statistics is it is 107.2, and the p-value for the F statistics, or the ANOVA test here, is 2.2 e raised to 16. So this test, whether the model is better than no model at all. Okay, and since the p-value is extremely small, the model is statistically significant, and height explain weight better than random noise. Okay, so this is actually saying that, so here for the above example, like Jeff Bezos, if he toss the coin and choose a model, he don't need to go for a random model, because this p-value is actually satisfying. You can go with this model. Okay, this F and P models are saying that you can go with this model rather than any random noise. Okay, so rather than a random noise, this random noise, this model is actually giving some good prediction. Okay, that is what this F statistics and P value says you. Okay, so that is what we have here. Any question here? Any questions? And the regression analysis or explanation? Okay, and I forgot to tell you one more thing that is also important. What is the difference between multiple R square and adjusted R square? So this is a classic confusion question in this, interviews and all. So multiple R square is the coefficient of determination. Basically, multiple R square measure the proportion of total variation in the dependent variable that is explained by the regression model. Okay, so it is actually give you total variation, and the formula for multiple R square is explained variation divided by total variation. Okay, as you all know, and it will vary from 0 to 1, including both values. So now, one important property of R square is R square never decrease when you add more independent variable, even if they are useless. Okay, R square never decrease. Okay, that is the uh, property of R square. Now, for this one, we have adjusted R square. Adjusted R square adjust, as the name suggests, it adjusts the multiple R square by penalizing unnecessary predictors. Okay, so it will penalize the unnecessary predictors and adjust the multiple R square. That is why, that is the definition of adjusted R square. Okay, it will penalize unnecessary predictors. Okay, that is the terminology or definition for adjusted R square. Okay, it will penalize the unnecessary predictors as multiple R square won't decrease when you add um, more variables, even though those variables are useless in your prediction. Okay. So adjusted R square increase only if a new variable generously improve the model. Otherwise, it decreases. So that's why in 99% of the time you are seeing a adjusted R square will be always less than R square value. Okay. Any questions? Any questions till here? Okay. Now we will quickly check the assumptions of linear regression and we will conclude. Okay, so first assumption is linearity. So we will simply plot the model which equal to 1. So it will give you the linear versus fitted values. So there is no normal assumptions here. Okay, we will quickly do all the assumptions and then we will explain one by one. Okay, so first one is simply this one. So second one, normality of residuals. So that also we will plot using which equal to 2. So this is the QQ plot. Okay, so this is the QQ plot, and then we have third assumption. Uh, it is homoscedasticity. So that for that we can check the non-constant variance test. So for that NCV test function we will be use. So that will be, this is the chi-square values for that one. Now we will check the independence of residuals. That is, for that we will use Darwin-Watson model. Then for multicollinearity, yeah, we will use the VAF, variance inflation factor. Model contain fewer than two terms. Okay. Oh yeah, yeah. We only have one predictor, so VF is not necessary because um, VF is actually calculating between the uh, independent variable. Okay, so here we only have one predictor variable. That's so we don't need the VF value. So these are the main assumptions we need to check. Okay, now we can visualize the regression line as well. So here. Okay, so this is our, okay, this is our values together. Now we will explain one by one. Okay, so here the first thing is yeah, first the linearity. So here this residual was fitted value plot. Okay, so this is actually help us to determine the linearity. If there is any confusion we can actually go for another test. So here it is very clear that okay. So here it is very clear that the residuals and fitted values are scattered around, and so this is actually showing a random scatter around 0. Mm, okay, it's very scattered. no curve or funnel shape, this is there, so it is uh, a roughly constant spread. It's not a constant spread actually. It's a There is no strong patterns is actually showing here in this one. So linearity and homoscedasticity is satisfied somewhat. Okay, and when it comes to the QQ plot, for the normality assumption, we use the uh, QQ plot. So there, points are close to the straight line here. If you see, points are close to the straight line. So mostly follow it in the diagonal and minor tail deviations here and here. So approximately this is normal, and in real life scenario we won't able to expect the complete normal one. And when it comes to the assumptions for homoscedasticity, so here NCV test, constant variance test, that is actually failed to reject the, as the p-value is greater than 0.05, it failed to reject the H naught. So the variance is constant here. So homoscedasticity is okay. And independence, Durbin Watson's test for independence, so there also p-value is greater than 0.36. So here we can conclude that there is no autocorrelation. So errors are independent, so that is good. So that also satisfy. So multicollinearity is not applicable for a single linear regression. So simple linear regression, we don't need a multicollinearity, so we don't need this one. So uh, we have all the assumptions satisfied for the regression model here, even though it's a hypothesis model. And you can also see the regression plot of the actual values, and here also most of the variables are actually scattered around this plot and in um, a rough linear trend. Okay, it's not a clear linear trend, but it is having a rough linear trend, and only some exceptions are there. So this is actually a good model with the given r square. Okay, so we can iterate the models and all. So here the multiple r square indicate 52.39% of the variation in weight can be explained by height. Okay, and yeah, and adjusted r square also account for 51 percentage or 52 percentage closely. Um, and so the f value, f statistics and p value for that one also telling like even the r square models are small, the model does not suffer from overfitting and all. And this is a meaningful predictor. We can iterate the model and we can boost the model a little bit better. But overall this is a fine model, not a good model, it's a fine model. We can use it for prediction. That is the interpretation from this model with all these inputs. Now I'll stop here for today, and if you have any question we can discuss quickly. I know it's almost 1:28. Okay, we are close to the time. Any questions, we can address it. Okay, one question is there. So how to increase the model efficiency, since you earlier said it's only 50-50? Yeah, for model efficiency, we can actually tweak the models and all. So we will explain those things in tomorrow's session. We will continue from here, how to increase the model accuracy and all. And then we will move for the generalized linear model. Also, sometimes when we tweak some parameters and do some transformations and all, and then also if the model doesn't, so those kind of things we will be doing, like we will tweak the parameters or variables and all, and then we will simply yeah, we will simply do some transformations and all. And so in that case, if the model doesn't fit, so that means the linear regression won't be appropriate for that model. So in that case, we will go for the another type of models. So basically, I'll just explain quickly. So increase the model efficiency here. That is simply mean improving three things, or yeah, three things. So one is the adjusted R square value we need to increase. Then residual standard error we need to reduce. Then we need to improve the prediction accuracy. So sometimes we can actually do some transformations or add additional values and all, or check for some non-linear relationship, like instead of direct weight into height, we can also okay, here we put weight into height. So instead of this, we can also put some transformations and all, or some weight and all we can add. So that might support the things, or we can change the weight into log of weight. So let me check, log of weight will support this. So here we can update a model like this. Okay, so here I updated the weight into log of weight, so that doesn't make any change much. And also I can do some other transformation, like taking the inverse and all, so those kind of things, or add additional variables, and also or stabilize the variables, like mm, log of weight is not worked, so let's see log of height, or we can take the square root of some values and all. So log of height is also not worked. So okay, that is also not much changed. No, it actually changed slightly, but not much. Or we can do some transformations like this, like I of height square, not much like so. So we can do these kind of transformations and things. So also we can try to reduce the noise. We can actually plot model. So if we plot the model here, okay, okay. So this residual plot, this is the one. So here we can actually reduce the noise of residuals, and also those kind of things are actually there. So we can definitely look into those things tomorrow. Okay. And if all these things here, you already seen, like we have tried a couple of models here, like a couple of transformations and all, and then also it didn't work. So in that case, actually linear model, simple linear regression model is actually not suitable for this data. So we need to look for other models, like let's say some uh, ridge regression or penalized regression and all. So those kind of things we can definitely try, and we can see those things. Okay, so that is about the models. Any other question from anyone? Okay, so here yeah, this is the attendance for today. So uh, this is the attendance sheet for today, and okay, so this is the statistics for the attendance today. Okay. As always, this will be taken into consideration for your final result and all. There will be definitely a weightage for attendance and assignments.